In the last lesson, we saw how we could solve polynomial equations algebraically, and now we're just going to extend that to solve polynomial inequalities algebraically. So if we want to solve something as linear, like the one that we can see in example A, as in no exponents on the variables, all we have to do is just follow the same rules as we would as if we were solving an equation. So in other words, we can add numbers to both sides, we can subtract numbers from each side, we can multiply, we can divide both sides. The only difference is that if we multiply or divide both sides of an equation by a negative number, we have to switch the direction of the inequality sign. So I'll show this actually in the second example. Let's start with the straightforward then. So we're going to treat this just like it's an equation and solve it accordingly. I want to isolate x. Therefore, all I have to do is add 8 to each side. So I'll actually write it out. And obviously, at this point, we can do most of this work in our head, but I just want you to see exactly what's going on. So we're adding 8 to each side, and of course the negative 8 cancels the positive 8, leaving just x on the left, which is the whole point. And then 3 plus 8 equals 11, and x is greater than or equal to 11. Now, if I want to show that on a number line, remember, it's just for a variable like this, we can draw our number line out and put some numbers that will be in the correct range for what we're looking for. Put a few marks on here and an appropriate scale. So maybe 8, 9, 10, 11, 12, 13. Now if I want to represent something that's greater than or equal to 11, I put a closed circle at 11, and then I draw a line with an arrow on the end to the right. Let's take a look at this next one. Again, I want to isolate x. So again, I'm going to approach it like I'm doing an equation. So the first thing I'll do is I'll add 4 to each side. This time I won't write that down though. So if I add 4 to the left, it takes away the negative 4. If I add 4 to the right, I get 16. Sometimes we just describe that as a shortcut as bringing the 4 over to the right. Then what I want to do is I want to divide each side by negative 2. If I divide each side by negative 2, I'm left with x on the left side, and of course I'll have 16 divided by negative 2 on the right, and I'll simplify that in a minute. But this is one of those cases where I have to change the direction of my inequality. Once again, it's because I am dividing by a negative number. If I multiply or divide by a negative number, I have to switch the direction of my inequality. And then when I finish it up, I get x is less than negative 8. So this is the step where we reverse the sign. And then again on a number line, if x is greater than negative 8, that means that I'm going to put an open circle on negative 8 so that I'm not including it, and then again I will go up from there. Now if I'm dealing with something that's not linear, such as this case here, example 2, it's a quadratic. It's in factored form, but this is a quadratic, and it's an inequality. We've seen that we can solve these types of things with Desmos pretty easily. And just to draw a sketch of what we're used to dealing with, we have zeros at -3 and at positive 1.5 from these two factors respectively. And it's a parabola, it opens upwards. I guess I could get the y-intercept easily if I just put x0 in for x. So 3 times -3 would give -9. Let's just mark that on here. Say that that's -9 there. And here's a rough sketch. And remember, if we're looking for where the graph is greater than 0, we're looking on the y-axis where it's above the x-axis. And then we're measuring, though, on the x-axis. So the part I've highlighted represents the part of the parts of the graph we want, but I need to actually measure it on the x-axis. So you can see that any x values less than -3 or greater than 1.5 would give us our solution. However, it's not always so obvious with a equation. It's not always quite as clear as this. So sometimes what we have to do is we have to use a table, which I'll show in the next one. But let me write out my answer here. X is less than -3, and x is greater than 1.5. All right, let's try one without graphing it. So this is an approach we can use even if we don't have any idea what the graph looks like. So this one again is nonlinear. This one happens to be cubic. We want to factor it and break it into its parts still. So when I look at this, the first thing I notice is that I could take out a common factor of -2. And then I can look at -8 and think about which values to try for using the factor theorem. So 1, 2, 4, and 8, plus or minus for each of them. And just to save a little time, I know that 1 doesn't work, but when I put -1 into the equation, it does end up equaling 0. You can confirm that for yourself, but I know that x plus 1 is going to be a factor. And then I can carry on from there to do some synthetic division. That means I can go -1 outside here. I can just use the coefficients inside the brackets, so 1, 3, -6, -8. Again, this is my remainder, and then the other numbers are coefficients of x squared, x, and constant term, respectively. So the next step down here, think of this as rough work, but the next step down in factoring would still have that -2 out front. I have the factor x plus 1 now, and that's times x squared plus 2x minus 8. And that's what's less than or equal to 0. And then I can factor the quadratic that I have left, just using the techniques we've learned in the past. Two things that multiply to give -8, add to give +2, would be a +4 and a -2. All right, so that's the first step, is we want to have it all broken down, and then we want to know what the zeros are. So from that, we can see that there's actually going to be 3 zeros. There's going to be x equals -1, -4, and +2. What this does is it divides the graph up into sections, right? Again, let's just go with the fact that we don't really know what the graph looks like. Let's say that we have no access to Desmos. We have no way to really tell, but we do know that we're going to have zeros at -1, at -4, and a +2. We also know that if we're looking for where this function is less than or equal to 0, we're going to want parts of the graph that are underneath the x-axis. So if I want to check this algebraically, here's a way we can do it. I can think of the graph being divided into 4 sections. Each time it hits a 0, it's crossing to a different section. So we got one section, which is to the left of -4, anything to the left of -4. We got another section between -4 and -1. And then we got another one between -1 and +2. And then we've got the last one, anything to the right of +2. So again, the graph is going to be crossing the x-axis at those 3 zeros, making 4 sections of the graph. Some of them will be above the x-axis, some of them will be below. The way we can check algebraically to see if it's above or below the x-axis is like this. We can make a table up. With basically showing each of these ranges. So x is less than -4, x is between -4 and -1, x is between -1 and +2, and x is greater than +2. So these will be columns in our table. Then we're going to take our factors and we're going to put them in a different row of the table. So even the constant factor -2 gets its own row. And so then we'll have x plus 1. Oops, except that I put it in the wrong. Sorry, I need to go a little bit farther to the right. I need to add another column here. I don't want to write it underneath the x less than -4. So -2 here, x plus 1, x plus 4, and x minus 2. Now I just want to think about, in this column, let's start with this column here. If x is some number less than -4, say -5, -10, -1,000,000, whatever, is -2 going to be positive or negative? Well, that's kind of a trick question because 2 is always going to be negative. It's a constant term, so it's going to be negative in this column. And it'll be negative in this column and this column and this column. -2 is always negative. We're just going to think about if it's positive or negative. Okay? So that first row, put negative signs all the way across. But let's go to the next part down. Let's say that it's x plus 1. If I put a number that's less than -4 in, so again, let's think of one like -10 maybe. So if I stick -10 in for x, then I'd have -10 plus 1 is -9. I'm going to have a negative answer overall. And that's all I'm checking for now. So I get a negative when I put -10 in here. What about if I put -10 in the next one down? Well, -10 plus 4 is still negative. It's going to give me -6, so negative overall. And same if x is negative, or it's x minus 2, I'm going to get negative for this one as well. If I go through and do each column this way, so move on to the next column, pick a number between -4 and -1. Any one will do, it's always going to give the same answer. So let's say we go with -2 here. All right, so -2 plus 1 is going to be -1. It's going to be negative overall. -2 plus 4 is going to be positive 2. So down to this row, -2 plus 4 is positive 2. So this is the first time we've seen a positive outcome, but there's going to be lots more. -2 minus 2 is going to be negative once again. and then we carry on. Pick a number between -1 and 2. 0 is probably the easiest one. If I put 0 in for x plus 1, I get +1. 0 in for x plus 4, I get +4. And the last row, I get -2. Finally, pick a number greater than 2. Again, an easy one would be just +10. I get +11, +14, and +8. So I've got all these signs, and after we do this a little bit, we get a bit faster with it. What we want to do then is combine these signs. So imagine if we're multiplying all these signs together, because that's really what we're doing with each of these factors, is we're multiplying -2 times what's in the first bracket times what's in the second bracket times what's in the third bracket. So when we multiply a negative times a negative times a negative times a negative, so in other words, these 4 negatives vertically, overall, we're going to get a positive number as our outcome, because an even number of negatives will give us a positive as its outcome. And then if I were to multiply these ones together, 3 negatives and a positive, well, I'll start from the top. Negative times negative is positive, times the positive gives positive still, times the negative gives negative overall. So we're just determining overall, when we combine all our different signs, whether we're going to have positive or negative for that part of the graph. Negative, positive, positive. I got 2 negatives, and really that's what I'm counting. I'm just counting how many negatives do I have. Even number of negatives will give me a positive, an odd number of negatives will give me a negative. So 2 negatives makes it positive. The last column, I've just got a single negative, so that's going to be negative overall. So how do we interpret that? Well, remember the question was asking us, we want to find when the function is less than or equal to 0. So that means we're looking for parts where the function is going to be a negative number. On the graph, it would look like something below the x-axis. And below the x-axis corresponds to negatives overall. So now we have our intervals. We know which ones are the correct ones for our answer. And so the solution is that x has to be between -4 and -1. And remember, this does include the equal sign underneath, so I need to include it here. And x has to be greater than 2. Those are my only possible answers. Graphically, it's going to end up looking like this. But it's a way of doing this without requiring a graph.